This Kiat, he has been very worried about the exam. Don't worry about the exam, at least. So there will be 4 problems and a bonus problem. 3 of the problems will be very similar to homework or similar enough that you have to think a little bit. It won't be like direct copy. So if you decide to like copy every homework solution on a cheat sheet, that does not mean you get 75% of the problem. You still need to think just a little bit. And there will be one problem which will be new. And that will be similar to the type of things Chandler has in exercises and things like that. If you need practice problems, just go through Chandler's problems and look at it. And there will be one bonus problem, most likely. I cannot promise. But if there is a bonus problem, please do try it. So yeah, there will be 4 problems. The idea being that you have 30 minutes for each problem. It should take shorter than that. And any more questions? So everyone's going to get a B minus. If you totally screw up in the exam, and I feel like someone is going to push me to the limit on this. Maybe Omar will do that. He'll be like, okay, I will not come to the exam, something like, don't do that. But you will still get a B minus. So because all of you have participated enough. So I think everyone deserves a B minus at least. Now, whether you get an A or A plus will definitely depend on how well you do in the exam. If you do very well, you could get A or A plus, and so there will be a range. The exam will decide the range between B minus and A plus. Yeah, so Kiat, I was just talking about you. You can check the video later. So today we will do a wrap up of the very brief introduction to the renormalization group. I mean, we really scratched the surface. It's a huge, big topic. You can read about it online or there are lots and lots of resources you can read on it. So I just tried to give you a flavor and I will finish it. Then I will do a quick recap of the semester. I'll go through the main topics, the big picture ideas that we have done, the things that you can remember once this course is over. And please submit your course evaluation. So far, only 30% people have submitted. I would like to really get up to 90%. Oh, I had not written much. See, it's been a long semester. I'm tired. Okay. Yeah, I've not written much. It's just a sad face. Okay, so let's recap where we were with renormalization group. So the idea was that if you have a Ising model where the energy of a given microstate is given as minus interaction term J, Si multiplied by Sj, and only nearest neighbor interaction. And if you want to calculate the partition function for this thing, n comma t, there is no volume in an Ising model, and this is equivalent to thinking about n comma k, where k is defined as beta multiplied by j, or j divided by kbt. Then this Hamiltonian, this partition function is summing over all microstates e to the power minus beta e mu. And this is going to be really complicated because summing over all microstates means going to every spin S1, S2, S3, Sn equal to plus minus 1, and then doing e to the power minus beta minus summation I minus j is equal to 1 summation j Si Sj. So, right. So, I mean, maybe one of you thinks that this is not a complicated integral, but I would like to argue that this is a really, really complex, sum. This is a very complicated sum. So it's hard to calculate. So we started introducing renormalization group by looking at 1D Ising model. And in 1D Ising model, you have spins 1, 2, 3, 4, 5, 6. So why am I covering renormalization group, even though it's not going to be on the exam? Because this is a powerful concept. You will come across it sooner or later, especially not just biological systems, but everywhere. The idea being that many physical systems tend to have a scale invariance, whether you are looking at, okay, so if you're looking at a material at a nanometer level, right, then maybe quantum mechanics holds true. But once you go from nanometer to micrometer to millimeter, does the physics really change? At some point it starts to change, but there is a range in which, physics persists. You can make it 10 times larger, 100 times larger, 1,000 times larger. Sure, at some point, classical mechanics holds true. At some point, non-Newtonian fluid mechanics starts to hold true. But in any physical problem, you can get away by changing the range a little bit. The physics stays the same. So here what we do is to average out the behavior of all even spins. So we call it the decimation procedure, By decimation does not mean that we just go and kick it out. No, we realize that, and this is the physical picture you need to remember, that as per this energy Hamiltonian, this energy microstate, 1 talks to 2 and 2 talks to 3, right? So it's like, I mean, I'm in a box and I can talk to the person in the other room, right? And I cannot, there is another box after that, another box after that. I cannot talk to the person 2 boxes away from me, but I can talk to the person in the next box, and this person can talk to the person in the other box, right? So in a sense, I am talking to the third person, right? In a sense, everything is talking to everything else, but 1 is talking to 3, mediated through 2, right? 2 decides how 1 talks to 3. So what we are going to do is to average out the behavior of all even spins. We will say that, well, 1 talks to 3. And how can 1 talk to 3? 1 can talk to 3 when 2 is equal to +1, or 1 can talk to 3 when 2 is equal to -1, right? 2 has only two possibilities. Same thing for 4, same thing for 6. So we are going to, we averaged all of this out. I will not go through the math again, but then we got a relation. So when we average the even spins out, we started with capital N spins, and we are going to be left with n/2 spins, right? And the relation that we showed was as follows. We showed that Q of Nk, and again, to remind you, K is nothing mysterious. K is just beta multiplied by J. So it takes care of the temperature, it takes care of the interaction parameter. And you'll see why it matters. So Q of Nk is equal to some f of K, where K does not depend on the spins. It is, and I will write down the value of what it is, multiplied by summation over S1, S3, S5. So no S2, S4, S6, they have been averaged out. E to the power K prime S1, S3 plus S3, S5 plus ... So it's like the original partition function has been mapped into another partition function, which is just like an Ising model, but with half the number of spins. And there is a prefactor. And we know for thermodynamics, we generally don't care about prefactor, right? Because it's when you take log and you differentiate it, it goes away. So what was K? So we have two things here, right? We have this f of K and we have K prime. And we derived expressions for this. We said K prime, because what we know is K, right? We do not know K prime. We do not know F. So K prime turned out to be half of log of hyperbolic cos of 2K. You don't have to remember this, okay? Don't worry about it. It's not in the exam anyway. So this was equation 1, and f of K was related to K through 2 of square root of hyperbolic cos of 2K. So we had these two equations. Then we introduced a free energy, which is intensive. So we introduced G of K, that is defined as 1 by N log of Q of Nk, right? Let's call this equation 0. So if you take log of equation 0, what does it look like? So log of equation 0, that gives us ln Q of N comma K is equal to half N ln F of K plus ln Q. Now this term that we have over here can be written as Q of N by 2, because we have half the number of spins, and an interaction term, which is K prime. And again, K introduced temperatures. K includes temperature and the J term. So it has both, right? So we have this equation. And now we can divide both sides by N. If we divide this one by N, we divide this one by N, we divide this one by N, what are we going to get? The left-hand side will become G of K is equal to half ln F of K plus half G of K prime, or G of K prime is equal to 2G of K minus ln of 2 square root of hyperbolic cos of 2K. And this is known as the central RG equation for an Ising model in 1D. Okay, so this is the central RG equation. So this looks all abstract, but now let's put this to use and see what it can do for us. Okay, this is all abstract, but you'll see why it's really powerful. So let me write down that equation once again. So central renormalization group equation is G of K prime is equal to 2G of K So what is the idea here? The idea here is that we know how K prime is connected to K, right? K prime is half ln hyperbolic cos of 2K. So if two systems, and I keep repeating this because it's easy to forget what K is. If two systems have different values of K, what does that mean? You could keep the same temperature, right? Same beta, and have two systems with two different interaction parameters. Their free energies are going to be connected through this simple relation. And this should surprise you. This is a powerful relation, right? Because in order to get the free energy, you have to calculate the partition function, you have to take the log, you have to do all that business. But this is telling you that if you have two Ising models where beta J values are given, their free energies are going to be connected through this quite simple relation. It's not simple enough that you can do it in head, but on a calculator, it's very, very easy to do. So how do we get started? So the idea is we will actually start with a K prime, which is very, very small. Then calculate a value of K and then keep moving and see how it allows us to calculate every value of K. So what's the smallest value of K prime you can think of?
0.
Why not smaller than that? Why not negative? No, it can be negative because J can be negative, right? So in principle, we could do that, right? There is nothing stopping us from taking a negative J, right? We could do that, but here we'll start with 0. Okay, we will focus on the positive J domain. So if K prime is very small, that means beta J is very small, right? Beta J prime, whatever that is. So this means that either J is very small and or beta is very small, right? Beta very small means T is very high. So we have a Ising model where temperature is very high and the interaction term is very, very weak. If you're really ready for the exam, you should be able to answer my next question, okay? If you can answer my next question, then you don't need to prepare for the exam. You'll be just fine starting from now. What is the partition function for an Ising model? When J tends to 0, there is no interaction. H, we have already said 0. There is no external magnetic field. And T is very high. And we have N spins. So what's going to be the partition function for such a system? Huh?
1.
No, think closer. What is partition function? Let's go carefully. Why did you say 1, Nathan? Tell me, what is the definition of partition function? We go to every microstate, right? And we calculate e to the power minus beta E nu, correct? How many microstates do we have? Suimin answered this last time. 2 to the power n, right? And what is the value of E nu? E nu is minus J summation Si Sj. So if J is equal to 0, what is the value of E nu? 0, right? Now, can you tell me what is the value of Q? 2 to the power n. You are going to every microstate, 2 to the power n microstates, and you're doing 1, right? So Q is 2 to the power n, which means that we can, for a very, very weak Ising model, we can write down the partition function, right? There's nothing to do there. So now we can get started. And we can put the machinery of renormalization group in action. So Q of 0.01 is equal to 2 to the power n. We are interested in the intensive free energy, right? Free energy per site. So G of 0.01, what is the definition of G? G was 1 by n log of Q, right? So that's going to be 1 by n log of Q, which is 1 by n log of 2 to the power n. How much is that? ln2. What is the value of ln2? Yeah. Why did you say 1.4? That's E.
That's the rule.
It's 0.693147. I don't remember that actually. So, but I have it in my notes. So G is G of 0.01 is equal to 0.693147. Okay, so let's go to the next page and write down the information we have so far. So Q of 0.01, and I'm going to write things on the left, and I'm going to make a table on the right side. On the right side, I will have the value of K. I will have the value of G of K as per renormalization group. And I will tell you what is the value of G of K if you did an exact calculation. And you have to take my word that the Ising model can be solved exactly in 1D and in 2D, right? We did not do that. How did we solve Ising model? We look at the intuitive pulse droplet argument. We looked at mean field theory, right? But if you go and look at Chandler's chapter, the first problem in the exercise is actually solving it in exactly. I'm not going to do that on the exam. Don't worry about it. But you have to take my word that in 1D and 2D, Ising model can be solved exactly. In 3D, it's still an open problem and in higher dimensions. No one has been able to do it. So Q of 0.01 is equal to the power n. And G of 0.01 is equal to ln2, right? So what we want to do now is basically we are starting with K prime is equal to 0.01, right? That's what we did. We set our K prime is equal to 0.01, and we are going to back calculate K. So we had this equation, right? Connecting K prime with K. So we are going to use this equation to back calculate K. So K prime is equal to half ln hyperbolic cos of 2K, right? And you know the value of this one. This is 0.01. So you can calculate the value of K, right? It's just one line of algebra. When you do this, you will find that K turns out to be 0.100334. So why do I care about this? So let's put in the values here. So I started with K 0.01, and this takes me to a value which is slightly larger, 100,334. And the value of G of K for this one was ln2, which is 0.693147. Now I need the value of G of K for this new K, right? How do I do that? For that, I have my central RG equation that tells me, right? Central RG equation says that if you know the values of 2Ks, you can go and calculate it, right? So when you do that, you get G of this new K, which is 0.100334, turns out to be 0.698147. So we can put that value over here, 0.698147. Now what can you do? You can take this K, which is 0.10034, put it back into this equation, right? And you will get another value of K prime. It's going to increase. It will keep increasing. When you do that, the next value turns out to be 0.327, and you get some other value of G of K, right? So you can keep doing this. At every step, it will keep increasing. At some point, so on the Kardanoff paper does this, so you can go and read it in more detail. You get the value 2.702196, for which you get the value of G of K 2.706633. Again, don't try crazily to capture all the numbers, but the main point I'm trying to make here will be clear in just one moment. So now if you were to calculate the exact value, you would find that for 0.01, the exact value is actually 0.693197. So it's already kind of close, right? But there's a small error. For this one, it is 0.698172, slightly closer. For this one, it is exactly correct. And as you keep increasing, it stays in exact agreement. So this is how people came up with an alternative way to solve for the Ising model for any value of K. And once again, what is K? K is beta J, right? So you can solve it for any value of temperature, any value of J. Now you're like, well, I didn't really need 0.327. I wanted the answer at 0.25, right? You don't have that answer, right? So for that, you would start with a slightly smaller value of K, right? It's a numerical procedure. You could make a plot of G of K versus K, right? And try to interpolate and get your values. But hopefully you got the key idea over here. So now something very interesting happens. If you do this, it keeps increasing until k is equal to infinity. It never stops. And that you can easily see from this equation, that k prime is equal to half of ln hyperbolic cos of 2k. If you look at this carefully, you will realize in a moment that it just keeps increasing the value of k. So you can make what is known as a flow diagram. In the flow diagram, you start with a small value of k, which takes you, it took us to some value 0.01. From there, we went to 0.1, whatever. You basically, you will keep increasing in values. I showed you how you got to 2.7, it becomes exact. And as you keep increasing it, you get to k is equal to infinity. So Kardanoff in that article calls it as uninterrupted flow. What does this mean? This means that the physics of the problem does not really change irrespective of the value of k. Okay, so you could keep changing the interactions and the physics is not going to change, which is what we saw for the Winding-Ivy. Have a phase transition. Okay, and I went at the speed of like gazillion miles per hour for this, but I really wanted you to get a flavor for what this is. And please read the Kardanoff paper if you want to see more about this. In 2D, we know there is a phase transition, right? So let me show you the procedure of just in 2 minutes, and then we'll go to recap of the semester. And Kardanoff does the 2D also in great detail. So in 2D, what would happen? So let's imagine a 2D square lattice, okay? So we have spins. We again need to decimate here. How should we decimate? We want to remove half the spins. Yeah, we can do it many ways, right? So we can remove this one. And we can remove this one. We can remove this one. We can remove this one. We can keep removing things like this, right? So what is the structure that we now obtain? Let me draw a few more ones over here. So we are removing all of this. So look at the lattice we just obtained now. Right? It's again a square lattice. It's very similar to what we did in 1D, right? In 1D, we stayed with a 1D lattice where everything was talking to its neighbor, but now it was hop over the first one. So this is again, looks like a square lattice, but the interactions are a bit more complicated. So Kardanoff goes over the math for all of this, and he makes the flow diagram. And the flow diagram for this one looks non-trivial. So if you start from k is equal to 0, you can keep increasing the value of k. You will keep increasing the value of k. And you will get to a certain value of kc. Once you go to that value of kc, you cannot go any further. You stop. And you have to look at the equations in Kardanoff's paper. So you can keep going in this direction. Once you get there, you stop. Because you don't have this log of cosine hyperbolic cos of 2k equation. It's some other equation where the algebra is such that there is a value of kc at which you cannot go further. Or you could start from a very large k is equal to infinity. And that would keep bringing it down. And again, it would stop at the same kc. So now you have an interrupted flow. And you have two different phases of the system. Phase 1 and phase 2. And you cannot do this idea of averaging out degrees of freedom and jump from phase 1 to phase 2. And that makes sense, right? Because what happens in magnetism? At very low temperature, you have every magnet aligned along the same direction, right? At very high temperature, you have magnets in random direction. So what it is telling you is that at low temperature, if you keep removing half the magnets, it still looks ordered, right? It still looks like a magnet where everything is pointing in one direction. But if you go beyond the critical temperature, that's not true. Now everything is random, and there is no way you can jump across the barrier, right? So people use this in multiple dimensions, and it's very powerful. There was a paper when I started here around 2016, it is by Schwab and Mehta, who I think both are at Northeastern. And this paper made a lot of noise because they showed that a very popular deep learning model, when you have these layers, all you're doing is to renormalize. And that paper made it like suddenly got 500 citations, then everyone forgot about it. This happens a lot in machine learning. Paper comes like, now we explain to you why machine learning works. And people are like, aha, this is why it works. And then next year people forget about it because it doesn't do anything, right? So this was one of those papers that made a lot of noise. You should read it if you're interested in machine learning as to why perhaps deep neural networks, when you have lots of neurons and you're doing things like this and you're compressing it, you are actually renormalizing interactions. So this was a classic paper that's interesting to read. So that's the end with renormalization group. I invite you to read more about it. There's a lot that goes on here. There's still a lot of research going on. We did not even discuss why it's called the group, or what are the group-like operations here. So we really skimmed the surface. Any questions about this? Yeah, Nathan.
Why do we only talk about an intensive free energy? How come we not talk about an extensive one?
Because if it's intensive, we can always multiply it by n and get the extensive.
Okay.
Because free energy is always extensive, right? So if it was some quantity that depended on n in a complicated manner, then it would be complicated, right? But we know free energy is extensive. Why is free energy extensive? Because, well, that's like the postulate, right? That's where we came from, our partition function that connects us back to thermodynamics. So we talked about intensive because free energy is extensive. So what's the point in dangling the n when we can always look at it divided by n?
Oh, okay, and I have a second question. So can you relate G of K to the Helmholtz free energy?
Sure, it's the intensive Helmholtz free energy. That's what it is. Okay, good. So I want to do a brief recap of this semester. We have been going for a while. We started in end of January. What was different in the world in end of January? What world events have happened since then? Russia was still in Ukraine. What else has happened? Anything that has really changed since then?
Wasn't in court.
Yeah. You guys watch too much news. How about something non-political? Nothing? Life has been the same? That's a boring statement. Kind of. This was a very warm January. Okay, if you can think of something, you can tell me. Please interrupt and tell me. Okay, so let's recap. So how did we start this semester? We started this semester by thinking about the concept of a microstate and how it connected with that of a macrostate. Why did we think about macrostate? Because last semester in 684, we talked a lot about macrostate, right? Last semester started by saying that there exist equilibrium states of a system, right? And there exists a state function S, which is unique in equilibrium, right? S of NVE can fully characterize it. Remember, then we had those partial derivatives, partial S by partial E, partial S by partial V, and all those things. So last semester, we talked about macroscopic properties. This semester, we started thinking about microstates, where the most accurate definition of a microstate is a point in phase space, which is R1, R2, R3N. So actually, let me write it R1, R2, Rn, and these are vectors, right? So each R1 is R1x, R1y, R1z, so on and so forth, right? So we have 3n such numbers. This is also known as the configuration space. And we have 3n momentums or n momentum vectors, okay? So total, we have 6n numbers. So the most accurate definition of a point in a macrostate, in a microstate, is if you look at P1, R1, P2, R2. So you have, in order to characterize a point in microstate, you have to characterize it with 6n numbers, right? While in macrostate, how can we characterize a point in macrostate? At equilibrium. Everything applies at equilibrium. So first of all, let me make it very clear, 687, everything is in equilibrium, right? We do not go out of equilibrium, we stay in equilibrium. So at equilibrium, what information do you need to characterize the macro state of a system? Huh? For example, NVE, right? Is that the only way we can characterize it? No, there are more ways, right? So we also had TP mu, etc., etc. So I can offer you a menu that you should remember. It's not food, it's the menu of StatMech. So anytime you want to characterize the macro state of a system, it's like you have the first course, and in the first course, you have to pick N or mu. Okay, you cannot pick both. If you pick both, you are in trouble. In the second course, you have to pick T or E, right? And the ordering of the course does not really matter. It's a funky restaurant. You can eat the dessert before the starter. And in the third course, you can pick V and P, right? And any three of these, that's an ensemble, right? That's one way of describing a macro state. This is the one way of describing a macro state. You could describe a macro state as mu PE, right? All of them are there. So these are different ways of defining the macro state. And why always three? Because in thermodynamics, we had three types of equilibrium. We had mechanical equilibrium, we had thermal equilibrium, we had number equilibrium, right? If you thought of a thermodynamics where you worried about information equilibrium, then you would have to define a variable related to information also, right? You would have a fourth line. But in thermodynamics, since we had three types of equilibrium, so when we say a system is in equilibrium, we mean all three apply, right? Unless otherwise stated, we know all three apply. So, and then we tried to form connections with this. So the one way we could construct a system is looking at NVE, and that's how we started StatMech. We called that as NVE. We called it as a micro-canonical ensemble. So what is ensemble? Clearly, if you are going to characterize a system with 6 n numbers on the left side, and if you're going to characterize a system with 3 numbers on the right side, there must be many, many possible values of the 6 n numbers that lead to the same value of the 3 n number, right? Does that make sense? So, you can think of it in many different ways, right? So this is all collection of microstates corresponding to one macro state, right? That's the idea. That's our ensemble. So ensemble is a collection of microstates. And we started by thinking about corresponding to, let me not call it one macrostate, but corresponding to macroscopic information. That's a better way. You can call it both ways. So it's corresponding to macroscopic information. So now we have to think about, so any microstate is generally denoted with the symbol nu. So nu is generally given by 6 n numbers. So then the question was, what is the probability of a given microstate, right? So we started with our microcanonical ensemble, and there came our first axiom or our first postulate. The first postulate was that P nu is equally likely for all microstates in a microcanonical ensemble. Okay, so if there are omega NVE states in your microcanonical ensemble that give you the same value of NVE, then P nu is going to be 1 over omega NVE. And we call this the law postulate of equal a priori probabilities. And this seems abstract, but it's really simple. Because if you're saying a system has constant number, so you cannot put a membrane and study how stuff is going in and outside it, right? If it has constant volume, you cannot put pressure on it and see how it responds to anything. If it has constant energy, you cannot put a thermometer and see how it is exchanging heat with the information, right? So you cannot do anything to the system. So the system is closed in every possible way. So if it's closed, you cannot do any experiments. I have to assume that everything is equally likely, right? That's where it comes from. So it's a simple probabilistic statement. So that was our first ensemble. And And that was our first postulate, the postulate of equal a priori probabilities. What was our second postulate? Or it might actually have been the first one, but I don't know. What was the other postulate that we talked about? Ergodicity, right? These two things are really what we needed to assume to get started. We did not prove these. We assumed these, that this is what it is. We take it as the word of God, and, the word of Chandler. May he rest in peace. Okay, so ergodicity said that time average is equal to ensemble average. So if you take a certain thermodynamic observable and calculate it as a function of time, and instead of that, if you prepare the system in different microstates with the correct probability, and that's super important that you prepare it with the correct probability. Are you preparing your cheat sheet already? Or that's okay. Okay, so these two are going to be the same. So what it means that if you have phase space P1, R1, P2, R2, whatever, and you follow a system as it goes, something like this, that's what you do in an experiment, right? You prepare the system in a certain state and you observe it as a function of time. In simulations or in theory, you don't do that because we don't have time. So, and this is so nice because there is no time over here, right? It says you can just calculate the system by preparing separate copies of the system at different points in phase space, and then not observing the dynamics as a function of time, but just observing one time. What is the value of the observable over there, right? So the big question now thus is, what is P nu? So we actually did ergodicity before microdynamical ensemble because this was the starting point. This tells us that we can forget about time and just make different copies of the system and calculate ensemble averages. Then the question happened, what is P nu? How do we calculate P nu? So if we don't know anything about the system, we have microdynamical ensemble P nu is equal to 1 over omega NVE. But so in that case, in NVE ensemble, average value of omega will be going to every microstate, dividing by 1 over omega NVE, which can be brought out of the summation and value of the observable in that microstate, right? And this opens up everything. You can now calculate whatever you want to calculate. I can create infinitely many problems out of this, right? That you can absolutely, whatever you want to do. But this is kind of a boring ensemble where you can't study anything. A better ensemble is NVT ensemble, where you have established thermal equilibrium, you are able to exchange energy in and out of the system, and you are studying how that is happening. In order to do this, many textbooks follow a different way. They look at this maximum entropy framework. We did not do that. What we did was to imagine the system embedded in a much, much bigger bath, right? So this is the system, and this is some bath. You can also call it as reservoir. And the whole thing is isolated. The whole thing together is an NVE ensemble, right? But this one is tiny relative to bath. So if this has, so E system is much less than E bath. And we did not need to talk about N system over here, but that's what we did for the grand canonical ensemble, right? So we did a Taylor expansion. Remember, we went through that. And through that, we got the P nu. And P nu for this one was 1 over Q e to the power minus beta E nu, right? This was NVT, where we can exchange energy, but we cannot exchange number. We cannot exchange particles. We went to the next ensemble, which was mu VT, where again, we have a bath. The full thing is isolated, and inside this you have something which can exchange energy, which can also exchange particles. So it's going to be at thermal equilibrium and mechanical equilibrium and number equilibrium with the bath. Okay, so and now we say that E system is much less than E bath, and N system is much less than E bath. Okay, both of these are very, very small. In this case, we get P nu. Anyone remembers the value of P nu? What? minus mu and nu, right? And we have a partition function z, which is now going to be a function of mu vt, right? So z is summation over all microstates, e to the power minus beta, e nu minus mu and nu. And all of these had their own connection with thermodynamics. You can calculate probabilities this way, and you can calculate averages. And once you calculate averages, you get nice connection with thermodynamics, which is when you have microcanonical ensemble, omega NVE, what's the connection with thermodynamics? Entropy, right? This is Boltzmann's formula. That's S, right? And you can see natural variables are preserved. Your knowledge of 684 is not challenged in this course. We are consistent with it. How about the canonical partition function? Helmholtz free energy, right? And here I have a minus sign if I, right? Minus KBT ln. How about the grand canonical partition function? And again, I think I had a minus sign. And this was also equal to plus PV or minus PV. Anyone remember? It was minus? Okay, I take your word. So this allowed us to calculate thermodynamics out of partition functions, out of StatMech. So notice something very consistent. It's always log of the partition function that gives us the thermodynamics. Okay, partition function blows up. We just did in the renormalization group, we calculated a partition function for an Ising model where there was no interaction, right? That's 2 to the power n. That just blows up, right? It's exponential. Log of 2 to the power n is, however, nicer. That's n log 2. It also blows up, but linearly, right? It just does not. So log is a nicer way to think about things. Log also plays a role. We will just get to that in a moment. But this is so the key message to remember here is that log of partition function gives us some state function, right? Depending on which ensemble you have, you get a different state function. But when we want to calculate average, thermodynamic average of some observable, apart from that particular state function, we end up taking first derivative of the log of partition function. Remember, we did it many, many times. What's an example of this one? In microcanonical ensemble, how would you get temperature? So what is the definition of temperature? 1 by T is equal to partial S by partial E at constant NV, right? And what is S? S was KB partial ln omega by omega E at NV, right? So you see, it was differentiating the log of the partition function with respect to something else. Statistical mechanics allows us to go one step further. It also allows us to calculate fluctuations in any thermodynamic ensemble, right? If we want to get fluctuations of some observable, we invariably end up taking the second derivative of the log of the partition function. So if you're looking at a problem and you know that you're interested in the first derivative, in some thermodynamic average or some fluctuation, and your partition function is some complex function multiplied by some prefactor, you can just ignore the prefactor if it does not depend on anything, right? Because you're going to take its log and you're going to differentiate it, right? So this is why the 1 over n factorial most of the times does not matter, but you might find in your exam that it matters. We'll see. So why did we do log? What was the benefit of log? That goes back to the microcanonical ensemble, right? We wanted S to be extensive. our thermodynamics told us that the entropy is extensive, right? When you add two independent systems, the entropy adds up, right? You happy, Aiden? Sure. Okay.
7 out of 10.
Huh?
7 out of 10.
Why? What's with the other three? One moment, Patrick.
I'm still tired.
Are you tired?
Yeah.
It's end of the semester. Yeah, go ahead, Patrick.
So for the microcanonical ensemble, the thermodynamic average of some observable is the first derivative.
Mhm.
What is the observable you're averaging to get 1/2? What's the corresponding observable? Like an east.
Thermodynamic average means average over all microstates. That's the average. So thermodynamic average in StatMech means you want to calculate the property in a macrostate and in a way that every microstate is accounted for. That's the idea.
But is there like an instantaneous temperature that you're like averaging over to give you 1/2 to give you the temperature?
Oh, I see, I see. No. There is no, that's a good point. It could fluctuate. In fact, we know that in, that's a good point. So yeah, you could define an instantaneous temperature. You could calculate, you go to this one and calculate fluctuation in your temperature, right? What will be the fluctuation of temperature? Here's the question. What would be the fluctuation of temperature in a canonical ensemble?
It's 0.
Zero. It's NVT. We have put a fixed temperature, right? What would be the fluctuation of number in a canonical ensemble? Again, 0. In order to get number fluctuations, we have to go to grand canonical ensemble, right? But by the same idea, in a microcanonical ensemble, temperature is fluctuating. Energy on the other hand is not fluctuating, right? Energy is fixed. Okay. So, and we looked at these examples of second derivatives. The first one was the heat capacity, right? Heat capacity came from second derivative of ln Q. Remember? So, and why did we use log for the partition function? Because we wanted our entropy S of NVE should be extensive, right? So if you have two systems, S of N1 plus N2, V1 plus V2, E1 plus E2, and they are independent, then this should be S of N1, V1, E1 plus S of N2, V2, E2. And we showed that log is the only function that has this property, right? Log came out naturally. You could not have defined statistical mechanics without a log. Log is the only function that has this nice property. It could be logged to some other base. We don't care about that, but it's a log. And this means that even for other partition functions, if you have two independent subsystems, if you have subsystem 1, which has partition function Q1, and if you have subsystem 2, which has partition function Q2, and if 1 and 2 are independent, then the partition function for the full system is going to be Q1 multiplied by Q2. What does this follow from? This follows from the extensivity of the Helmholtz free energy, right? Because minus KBT ln Q12 now is minus KBT ln Q1 minus KBT ln Q2, or A12 is equal to A1 plus A2, which we expect Helmholtz free energy to be, right? It's extensive. That's the definition, right? So the log is fundamental. There is no getting rid of the log. And now this leads to another idea as we move. And then we move. So we did all the basics, so you should definitely be comfortable with calculating fluctuations and things like that. In the homeworks, I even made you calculate third moment at some point. Did I make you calculate fourth moment in any of the homework? No, maybe I should. What do you think, Sumin? No? Okay, I'll listen to Sumin. But it gets nasty, right? You have to just keep differentiating and do things like that. But you should be comfortable with the second moment, second derivative of partition functions, because those are fluctuations, so they matter. So we did all the math, we set this up, and what did we do after this? We moved to independent systems, right? This was powerful because it shows if system is independent, we can do the partition function this way. And we tried to model everything using independent systems and actually got quite good results, right? We things that should not be interacting, we still modeled it using things that should be interacting, we still modeled it using non-interacting behavior, non-interacting partition functions, and it turned out to be quite nice. So we looked at phonons, we looked at photons, we looked at electrons, right? And more generally, we looked at Bose-Einstein and Fermi-Dirac. What was the main result that you should remember from phonons? Who was lazy? Einstein was lazy, exactly. So for phonons, the first result that you should remember is that so if you are plotting CV versus T, a purely classical system, classical harmonic oscillator, does not give us any variation in heat capacity, right? But we know that at zero temperature, heat capacity must go to zero because of quantization, right? Quantum mechanics tells us that there is an energy gap. So if you're at zero temperature, the smallest fluctuation that you give is going to be smaller than that energy gap, right? So quantum mechanics tells us that heat capacity should go to zero. So Einstein and Debye were able to derive expressions for this. The Debye expression goes as T cube, and then it goes over here, while the Einstein expression drops down too quickly and it goes over something like this. So this was Debye, and this was Einstein, which was roughly exponential, while Debye was T cube. So Debye got it right, and in order to do that, we introduced the notion of density of states. So be comfortable with ideas like that. How did we introduce the notion of density of state? How did it allow us to calculate the partition function? Okay, and density of state is something that StatMech does not answer, right? So StatMech, you wrote down the partition function. How did we solve this problem? We said that in the classical or in the quantum picture, we said every atom has 3 oscillators, right, along XYZ direction. So total n atoms have 3 n oscillators. And then we said, we don't know about the frequency of these oscillators, right? And that is something StatMech cannot tell us. How do we measure frequency? We do scattering. And you saw it in the midterm too, there were methods to do it, right? You can go and bombard it with neutrons, whatever you want, and you can see how the things are moving. And you can get a sense of this G of omega from experiments or from DFT, from density functional theory at zero temperature. That's why DFT, one of the reasons it's so powerful, because you can calculate it at zero temperature calculations. So you can get G of omega, and we developed a machinery of how to plug in this G of omega and get basically heat capacity, but you could have calculated other things also. You had the machinery to do that. For photons, what was the main thing that we calculated? We looked at black body radiation, remember? And we derived Stefan Boltzmann law. We saw the T to the power 4 dependence, and we calculated the temperature of the early universe, which was around 2 Kelvin or something like that, right? For electrons, we again went back to heat capacity. So for photons, we looked at U of omega, right? In black body, what is the energy coming at a certain frequency? For electrons, we again looked at the heat capacity problem, and electrons, the heat capacity problem turned out to be linear in temperature. Why did that happen? Anyone remembers? In other words, what are you seeing between electrons and phonons? Phonons, if the heat capacity is coming from phonons, which one rises quicker, T cube or T? T cube rises very aggressively, right? So for phonons, you're seeing that if you pump some energy, the heat capacity just blows up. It's like, yeah, give me more. I need more. While electrons, you can't do much. Why did this happen?
3 modes in X, Y, Z direction versus not that direction.
So which electrons could we excite? For phonons, we could excite everything, right? All 3n, exactly what you're saying. For electrons, so yeah, you said what is it for phonons, but how was it for electrons? For electrons, we had to look at the Fermi function, f of epsilon, right? And we said that if you have these levels, and we were looking at electrons in a metal, right? So a metal is something where electrons are occupied up till a certain level, then there is a gap, and and you might have some movement close to the Fermi level, right? That was the idea. So we have this Fermi level over here. So at T is equal to 0, the occupancy looks like this. At T is equal to 0, everything is occupied right up to the Fermi level, right? As T becomes higher, the occupancy starts to look like this. So at T higher, I will draw blue line on the same thing. You have some things that have jumped over. The deep levels still do not contribute. You cannot excite the deepest electrons level. You can only excite the electrons level which are close to the Fermi level. You can only excite the electrons close to the Fermi level. And we calculated that number through the area of a right angle triangle, and we got that, and heat capacity turned out to be linear in temperature. So for most materials, if you ignore phonon electron coupling, the heat capacity to a very good approximation at low temperature is given by AT plus BTQ, ignoring electron phonon coupling. So those of you who are going to work on fancy quantum materials and things like that won't have this luxury. You will have to worry about what happens when electrons talk to phonons. So we did this, then we moved to interacting systems. Oh yeah, and we also talk about Bose-Einstein and Fermi-Dirac, the quantum statistics. I gave you a sense for why the n factorial approximation comes out, how both of these reduce to classical statistics in a certain limit. What was the limit? Anyone remembers? There were two things: low density and high temperature. And this low density is super important, right? You need to have low density relative to what? Relative to the number of states, right? You saw in one of the homeworks. If you have only 2 states, then it doesn't work. You cannot just divide by n factorial. You have to be careful. If you have a lot of possible microstates, energy levels that can be filled up, then it will work. Then we move to fluids, where we have interactions. There we introduced everyone's favorite G of R, right? So we know that for non-interacting system, PV is equal to nRT, right? That's an ideal gas, but it's not going to be true for an interacting system. So G of R, the main way to remember G of R is that rho G of R is, Chandler says it is the conditional probability, but I don't really like it. I think it's proportional to the conditional probability. Probability conditional, it is proportional to the conditional probability of observing an atom at distance r from another atom that you know exists. So if you know that there is some atom, you can call it the origin, and then you are thinking about what is the probability, given that I have some atom at the origin, what is the probability of finding something else at a distance r? And I have quickly jumped to this spherically symmetric case. We did it for non-symmetric also. Don't worry about it too much for the exam. So we can draw this, and this G of R, so that's rho G of R, right? So if you are interested in G of R, that's going to be 1 for non-interacting system, for an ideal gas. For an interacting system, it will have complicated behavior. For a solid, it will have sharper delta peaks. But then it will again go to 1, okay? At some point, it won't be, so you can draw a curved line here. It will have more oscillations because you have so many neighbors, right? It will keep oscillating, it will gradually go to 1. For liquids, so this was for solid. For liquids, it will be kind of like solid, it will be more diffuse, but again, then it goes to 1, right? And for gas, it will be in between liquid and interacting system, right? Chandler has a photo of this. So we did this, and G of R is kind of similar to G of omega in the sense that it's something you can measure in experiments. What you can measure in experiments is really not G of R, it is the structure factor S of K, which is the Fourier transform of G of R, e to the power IKR. This is what you can measure in scattering experiments, and it was there in one of the midterm papers. We saw how to do it. So we introduced all of this, and then we showed a few things. I showed you how G of R is connected. G of R is connected to potential of mean force. We introduced that very important term, which is the idea that if all of us are non-interacting and I want to calculate the force of interaction, the force between Iden and me, and if you're truly non-interacting, there is no force, right? Iden ignores me, I ignores Iden, all is good, right? But if it's an interacting system, and if Iden and I are connected through a harmonic spring, then the force between Iden and me, if there was no one else in the room, then it would just be an interacting spring, right? But if all of you are also connected through harmonic springs, and Iden is connected to Sophia through an interacting spring and to Vanessa through an interacting spring, then it becomes complicated, right? And if I really want to talk about the force between Iden and me, I have to average over the positions of everything else, right? Because if Iden was connected through a spring through Sophia and through Vanessa and through a spring with me, just visualize it, and both of them are pulling him off in that direction, then he probably wants to be pulled off, right? Even though he's close to the equilibrium distance, he does not want to come closer, right? He's just getting pulled off. So the potential of mean force accounts for the mean force between two particles averaging over everything else. And that was related to G of R, right? We derived that expression. Anyone remembers what that expression was? It was d by dr of ln G of R. Remember, with a minus sign. So be careful with the minus sign. We had a homework problem with that. Then we used all of this and we introduced this very nice relation of free energy perturbation. And I believe many of you did the midterm, second midterm on the free energy perturbation and drug discovery paper, where the idea was that if you have an interacting system with a complicated interaction, you can map it as a sum of some reference interaction, UN0, plus some perturbation, UN1. The perturbation doesn't always have to be small. For any size of the perturbation, you can write Zn is equal to Zn0 exp of minus beta UN1 calculated in the ensemble, in the reference ensemble. This is an exact relation. You should be now, if you have understood StatMech, you should be able to close your books and derive this expression in 2 lines without having to look up anything. Okay, that's another, call it practice problem for you. You should be comfortable to do things like this. This is exact. We derived approximations to it when UN1 was small, right? If UN1 is truly a perturbation, we were able to do many things. We showed how we can get van der Waals interaction using Hart sphere as a reference, right? We use Hart sphere as a reference. We added some interaction, attractive interaction, and we got van der Waals. Hart sphere as, not Hart sphere as sphere. Okay, it's time to go. Hart sphere as reference plus attraction as perturbation. Those of you who saw, who here did their midterm on John Weeks's paper in science? Aurelia, you did it, right? Did anyone else do it? No, don't be scared, Aurelia. It's okay. That's great. It's a beautiful, I will tell John, you'll be very happy. Back in the day, you could publish a paper in science by doing only theory. Now, if you try to do that, they will be like, where is the experiment? Get out of the door. It's terrible. One day I will start telling experimentalist papers, where is the theory? Get out of the door. One day. So, but after the semester, if you have time, I recommend you go and read that paper. It was the origin of what is known as Weeks, Chandler, Anderson model, WCA model, which has been used to model so many things in science over the years. So this was free energy perturbation. Then we moved to the final topic, which was phase transitions. In phase transitions, we focused on the Ising model as an example of a phase transition, right? It has a very simple term for interaction. The machinery that I developed, you could do it for anything, right? You don't only have to do it Ising model, but Ising model was our test case to understand how phase transitions happen. So we looked at E nu is equal to minus J summation SI Fj, and specifically we focused a lot on I minus J is equal to 1. And we studied this in different ways. We looked at it in 1D, 2D, and 3D, right? And we did 1D, 2D, and 3D through 3 arguments, right? So we did 1D, 2D, 3D. What was the first argument we used for an Ising model? The droplet argument, right? That was the intuitive one. And what we are interested in is the value of the critical temperature, right? So what characterizes a phase transition? The first thing that characterizes a phase transition is the temperature at which the phase transition happens, right? What else characterizes a phase transition? Kinjal should know this. You did it in the rotation project. It's been a while.
Discontinuity.
yeah, how heat capacity and other observables, how do they change, right? So if you have a magnet and if you have a non-magnet, how they respond to external stimuli is going to be different, right? So the heat capacity will have different behaviors, and we did not really do all that. We just looked at the first thing, which is critical temperature. So for the droplet, 1D critical temperature was 0, right? Remember, we got the idea that why was it 0? Anyone remembers the physical picture? Go ahead. Yeah, which is because the entropy benefit is so much more. The energy benefit of the domain in 1D, even if you have a bigger domain, the domain boundary is kind of limited, right? It's only at the edges. It does not matter. So in 1D, entropy always 1. So we got a critical temperature of 0. What was our second theory? That was mean field, right? And the key idea in mean field was that on an average value of a spin I is the same as the average value of a spin J, right? So mean field is telling us that SIFJ is equal to SI multiplied by SJ. It is ignoring correlations. What did mean field do for 1D? It was disaster, right? It was terrible. Let's just write it terrible, right? It gave a critical temperature. So it's infinitely wrong. Then the third thing we did briefly was renormalization group. Renormalization group also gave us 0, right? That was nice. In 2D, the droplet argument actually came quite close. Remember, we did that. Onsager's was 2 by ln of 1 plus root 2, and the droplet argument was 2 by ln 3. It was really, really close. 3D we did not really do, but it works. So the droplet argument works in 2D and 3D. The mean field argument works in 2D. It really works well in 3D. And as you go to higher dimensions, it works extremely well. So mean field becomes exactly correct as you go to infinitely many dimensions, or as you start lifting this thing. Instead of only neighboring interaction, if you start having infinitely long interactions, it starts to become more and more exact. I did not prove these two statements, especially the second one is highly non-trivial to prove, as to why does mean field become exact in the presence of infinitely long interactions. It's non-trivial. You can read literature on that. And the renormalization group works well across dimensions. It works well in all dimensions. This is where we stopped. I want to point you out what to do after this semester. So after the exam, maybe 20% of you will hate me. I don't think you will hate me. You'll probably not like me that much. I hope it's not 20%. I hope it's 0%. I'm willing for that. Okay. So, but if you like it, or if you do not hate, even if you hate me, maybe you still like StatMech, right? So if you do like StatMech and you want to learn more, let me point out some resources for the future. So the one class that you should really, really consider, because many years from now, when you will be very old and look back upon your life, one of the things you might remember that you did at Maryland was to take non-equilibrium statistical physics with Chris Jarzynski. It's a true pleasure. And I hate it that I cannot take it because I have to teach the same damn time. So one of these years, next year I'm not teaching 687, but Chris is also not teaching 703. So it's kind of disaster. So Chem 703, which is intro, it's actually called special topics, but what Chris does is to teach non-equilibrium statistical physics, and it's taught every other year. So it will be taught 2 years from now. If you have interest, please take it. Don't audit it. If you audit a course, you don't learn anything. You have to go and do the homework. And he gives really difficult homeworks. He gives very difficult homeworks than I do. So I encourage taking it. I don't, especially if Chris teaches it. MIT has this open courseware. They have a lot of material on statistical mechanics from different departments, because, the power of statistical mechanics, it's useful for chemistry, it's useful for physics, it's useful for metallurgy, it's useful for material science, right? So MIT, you will find different courses with lots and lots of materials on this. And you can, if you're interested, you can also read Zwanzig's book on non-equilibrium statistical mechanics. It's almost the size of Chandler's book. It has a lot of typos. So, but it's a good book. It has no problems, but it's a good book to read if you're interested in non-equilibrium statistical mechanics. And there are more books in physics. There is a book by Patria, which is okay. There is a book by Kardar. If you are interested in thinking about chaotic systems and things like that, there is a book by Setna, James Setna, which is online. You can go and read that. So, statistical mechanics keeps growing more and more. There is so much material out there. I also really recommend some Nobel Prize lectures that you should read. The one that I would rank highest is the one by Ken Wilson, which he won around 1980 or so on the renormalization group. You should read that. So those are popular lectures, right? So they are designed for very general audience. Last year, Parisi won the Nobel Prize. You can read that one also. If you really want, you can read Prigoghine's lecture. Does anyone know who he? Has anyone heard the name of Prigogine? You have? Why? So he won it around 70s, 60s or something. So Prigogine is my academic grandfather. So he was my postdoc advisor, Bruce Burns' advisor. So when I joined my postdoc advisor group, I was like, wow, you worked with Prigogine. He goes like, yeah, that was terrible. He won the Nobel Prize only for political reasons. So even Nobel Prize has politics, believe it or not. So I say this one, maybe, I don't know. You can read it if you want, but it was controversial. These two I definitely recommend reading. And I will keep the Slack channel open for a few weeks, few months, whatever you want. And yeah, any questions? Before we wrap it up. So Saturday morning we'll be here, 7:55, nice and early. And I will have papers for you to write on. You just need to bring a pen or a pencil. You can bring a cheat sheet of this size. If it's slightly bigger, that's okay. If it's slightly smaller, that's okay. This is a very, I guess Alex is not here, but this is the question he asked in 654. They're like, I am unable to find A4 size sheet. What should I do? So you can bring a sheet of any size. I don't want to see your sheet. You can scribble in as much as you want, but don't push it to the limit. So in my hometown in India, where I come from, it's very corrupt. So, that's what it is. It's a town called Patna. So there was some exam where people had these sheets, and the sheet was basically the whole book. So they brought like super magnifying glass to read everything out of the book. So don't do that, okay? Don't push my rules to the limit. And the exam, 75% of the problems will be very easy. Please go through the homeworks. If you go through every homework, I have not posted solutions to all the homeworks because later towards the end, a lot of students were scoring 100. If you did not score 100 and you want to see a solution, I'll probably ask someone to volunteer and post their solutions. If you're comfortable doing that, if you scored full and you're comfortable sharing the solutions, please do that anyway. And so if you go through all the homeworks and you get the idea, then you will definitely score 75%. What does that mean for the exam? If you score 75% on the final, then you are definitely going to be B+ or higher, okay? So, but yeah, actually I did not say that. Then you will come in. Don't stress too much. I would like to be nice to you, give you easy grades. Don't stress too much. Don't blank. If there is a bonus problem, please try to solve it, okay? I will give you points. And yeah, so any questions? Yeah, go ahead, Kier. He's so worried.
First, 3 questions that you talk about. Is it, do they lean over like the first 3 homework or like?
I'm gonna have a special exam for Kier. Does anyone have objection to having a special exam for Kier? Raise your hand if you have an objection. No, not you. Does anyone have an objection? Looks like no one has an objection. Don't worry, Kier. You'll do fine. Don't worry. Okay. I know it does not. Yeah, you have an objection.
On behalf of.
Oh, look at that.
Chemical Physics and biophysics program.
Oh, we should take a photo. Does anyone have
I'd like to present you with this.
this will go for like treats for Pahora.
And more espresso.
Awesome.
How much is in there?
I don't know.
It's $1 million.
It's Mexican money. It has $1 million. Oh my God. Okay, good. So see you all